So let's look at your first homework. So the point is start looking at how to compare the growth rate of functions and then to learn how to do basic algorithmic analysis, okay? So the first two are the same type of problems. I give you two functions, f and g, and when n is a positive integer, that's what the z to the plus power is. That way we don't have to debate on whether or not 0 is a natural number or 1's a natural number. It's just positive integers, right? I want you to find the largest value of n for which f of n is less than or equal to g of n, okay? And then answer the two questions. Can we claim that f of n is big O of g of n? And is f of n equal to big omega of g of n? Okay, questions about that?
I have a question. Can we assume unless we have it twice found, either one of them can be true or no? Because right now, this one, we can say f of n is a big omega of g of n, right? Before the number of n that it is greater than g of n. Is it always two of them true or sometimes one of them? That's my question.
Well, I mean, it's possible. Well, technically, both of these could be true, or I guess in some sense, neither could be true, because what if you had something like this? It's never true there, right?
Okay. So how do we answer such a thing?
That's what we're gonna talk about today. So, let's go ahead and tell you that now, because some of you probably just crapped your pants, right? You went, wow, I don't have to do any of this. I got that in the last class. The reality is we have a compressed schedule. So that means in order to get homeworks in before test, and we only have time as it is now to get 2 homeworks in before the first test, is that basically I have to give you homework, and then we talk about the thing that you need for that homework that day, or at the latest Monday. That's just the way it has to be, because otherwise I would have had to have said, okay, we'll have a midterm and then have a final, and that means a lot more material for one test, right? So I prefer to have 3 tests overall, but that also means we have to cover things right on the fly, okay? So don't worry, we'll talk about that today, all right? The next 3 problems are also related to each other. So in each case, I'm gonna give you a code snippet. And what I want you to do is find a function of n, at least for 3 and 4, it's just a function of n that represents the total cost of executing this code, okay? And I want you to simplify the answer. So, of course, I did mine in parts. So if you said, well, the way I do mine is like f of n is equal to n plus another n, we'll simplify that. I don't leave it as a bunch of things added together. Tell me it's 2n. That's what you get, all right? And then once you've done that, find the big O value for that f of n. Right? So in this, you'll notice I've taken the for loop part, the top part, with the 3 components, and I've written them with separate lines, which is legal. But I did that also to show you what cost I'm associated with each one, all right? We'll get into this more, but ultimately, you know, are there real costs associated with things? Sure. But the type of detail it would take to know a true cost would be horrendous to try to really do, you know. Or you'll get down and say, well, my compiler happened to turn this into this assembly language, and on this processor, that means it was 2 clock cycles for this part, and 4 clock cycles for this part and this. I mean, in reality, that's true, but that's just really rough to try to do the calculation. So it's normal for us to make certain assumptions, especially in cases where we can't necessarily know how things are going to be. And I've already given you the assumptions, so that way we all get the same results. But what I'm telling you here is that each time you execute I equals 0, it's going to cost of 1. Each time we evaluate I less than n, it has a cost of 1. Each time we execute I plus plus, it has a cost of 1. And each time we execute sum plus equal I, it has a cost of 1. Your goal is to figure out what that total cost is as a function of n. Because since I don't tell you what n is, it is a function of n, right? All right? Questions about that? Number 4, same type of thing. Notice here though, on number 4, inside the loop, it's just a while loop, and in that sense, it's not really different than the previous one, although it makes it a little easier to write. But inside the loop, I asked the question, is I mod 2 equals 0? And when the answer is yes, or when that's a true statement, then we perform sum plus equal I. So really what I'm asking is say, okay, whenever I is even, you're gonna update the sum. which means depending on what you have for n, you won't be updating the sum every time you ask the question, right? Now, to make this a little easier, I told you to assume n is even. You don't always know those things, so sometimes we work with ceiling functions or floor functions. Okay, because there's gonna be certain things. So for example, when we start looking at divide and conquer approaches to things, they'll say, okay, take the data and split in half. And you know what that means. But what if the array has 5 numbers in it? Well, you don't say 2.5 of the numbers go here and 2.5 of the numbers go here. Well, something has to give, so you get 2 on one side and 3 on the other by using one of these functions to push things one direction or the other for whichever side you want to split on. Okay, things like that. And technically, you could do that same type of thing here, but I'm making it easier on us by just saying, we'll assume it's even. Okay, questions on that? And finally, for the last one, I've taken the entire part that says I equals 0, I less than n, I plus plus, and said all we're gonna look at is the I less than n part. Okay, that has a cost of 1. So you won't calculate any component for I equals 0, and you won't calculate anything for every time you execute I plus plus. It's very common to do that, because ultimately all they do is scale, because the number of times you do I plus plus is about the same number of times you say I less than n. So if you counted I plus plus, you're basically doubling the count, but it's still a scalar multiple of some growth. Okay? So notice that goes to n. The 4K part goes to p. Okay? And I didn't tell you n and p, so now you're ultimately going to produce a function of n and p. It says you tell me what they are, and I'll give you a cost. Okay? Because here we're also going to be checking to see now if the sum I plus k is even, and then we'll update the sum when it is, okay, which will add I plus k to it. So now you're on part A, you're going to find a function of n and p both. It's a single function for those, and then find the big O value for that, which will be in terms of n and p, since the function is in terms of n and p. Okay. I mean, real world code, while there's certainly times that both loops would go to the same number, right? They both would be the end, but certainly you've written lots of nested loops where they didn't both go to the same thing. Okay? Questions about that? All right. That'll be done in a week. Any questions? Because I want to turn off the projector. And once I turn it off, so I can back on.
You want that on a hard copy?
Yes.
Okay.
Right. As opposed to like seeing it through whiteboard.
Yeah.
Because I want something I can mark up. So last time we ended talking, we were comparing functions and determining order of the growth. So let's pick up from there. So it's common to see this. Oh, by the way, it's just because it's in my mind. So I asked that the Echo 360 be turned on, and they've done that. So it should start recording today's lecture. But realize I have no control where the camera's at. So it's quite possible it's filming that corner over there. All right? I can't do anything about that. All right, so onto this. Common to see something like this. And of course, you don't really see g in there. You would see n cubed or n log n or whatever the actual function is, okay? But this is kind of misleading. All right, the equal part. Because it's making you think I'm saying, oh, f and g are equal in some sense. What it really means, probably what people should have been writing all along, is this. Set membership. It's about a class of functions that in this case are bounded above by some scalar multiple of g once you get to a certain point. Okay, that was the n naught part. All right? So one of the things that hopefully will help help me too from this author. I don't know how she pronounces her name. I don't know if it's Bassey, Boss, Bass, I don't know. Start here. Question?
What exactly is GMN in this context? It's just some function?
Well, it's still that function that we're using to try to bound what we're looking at, right? I mean, the whole point of this is, ultimately it's going to come down to this, is that we're gonna say, I got these two algorithms. I mean, the reality is, you go get a job, you're not gonna sit down all your code and do an algorithmic analysis, okay? You're not gonna sit there and do that, because one is too difficult, and hopefully you've gotten better at programming by then. But you say, okay, I got a choice between these two algorithms. Which one do I choose, okay? Well, of course, you want the quote-unquote better one, or better is debatable, right? You can come with different criteria about which one might be better than the other one. But listen, if you're talking about speed, well, then you probably want the one that's faster, right? You say this one takes, like my example last time, quick sort took less than a second to sort 100,000 random integers on my laptop at home. Bubble sort took 43 minutes. I know which one I want to use if I have to go that route. But how do you compare them? Well, if we say, like in that case, quick sort was big O of n log n on average. It still has a worst case of n squared, okay? And then bubble sort was n squared on average. But depending on how it's implemented, it has a best case of n. So if you're saying, well, I don't know anything special about my data, I don't know if it's already partially sorted or what, I'm just gonna say, in general, which one's better. And if by better, I mean faster, I want the one where as n gets bigger, the cost is gonna creep up, not the one where it shoots up real fast, right? So in this case, if you say, if I'm really comparing two different functions here, well then, if I say one of these is bound above, so whatever quicksort really is, so quicksort is this, so let's say the true n log n, because this may be, there may be other calls, but let's say the true n log n is this. Okay, that tells you that something's not growing any faster than this. And the true n squared may be this. So it says, oh, this isn't growing any faster than this, but boy, that's a lot bigger than this. Okay? That's what it comes down to. So let's look at the diagram here. Now, when I first saw this, I was thinking, oh, is that right? Shouldn't the big O be at the top? Because we said big O is an upper bound. But look at where G is at, the thing we're comparing it to. It's right here. So if we start at the bottom here, big O says functions that grow no faster than G of n. So it's things that are at G of n's level and below, right? This is a rate of growth. So things that grow slower than G of N are below G of N, which means G of N is above those things. Right? If something's down here, then G of N has to be above it. So it's saying it grows no faster than G of N. If it passes G of N at some point and keeps staying above it, well then you can't say G of N bounds it at the top. Okay? And on the other side, if we talk about big omega, it says functions that grow at least as fast as G of N. Okay, G of N now is on the bottom. It says, oh, these things are faster. So if I were to look at this over here, I would say, oh, well, N squared, we could argue has a big omega of N log N. It's not saying it's moving the same rate as this. It's saying this is a lower bound. Okay, but a better lower bound for this would be N squared. Okay, because it's tighter. I used the analogy in the other class that if I was trying to estimate how long it took you to get here today, and I said, what was your average speed? You said, oh, it was less than 1,000 miles per hour. Well, that's true, but that doesn't really help me, right? It's not tight enough. You said it's less than 30 miles per hour, I got an idea of how long it took you to get here. And then we said, if the big omega function that we find and the big O function we find are the same function, so they're both N squared, they're both N log N, whatever, then we can use big theta, which says it's functions that grow at the same rate as that function. Right? That's what we're talking about being sandwiched before. Right? If they're two different functions, you say it's bounded above by N squared and bounded below by N log N, well then I can't say theta because it's two different functions. Questions about that?
Explain again about the, even though O is the upper bounding y, so it's like just.
Okay.
Like,
So yeah, here. It's a class membership issue. This is really describing what it is. If it says f of n is in this class, what's this class? It's the functions that grow no faster than g of n. So really, so we say big O is up here. If the function grows at this rate, or this rate, or this rate, as n increases, all these are really below this, right? I mean, if they're always this. Now, if you get some point where it does this, well, then it's not true. That's why we had the n not part, because we saw functions already where, you know, say it starts up here, so up to this point, this one's the higher one, right? But if we say we reach a certain point where a scalar multiple of this function is greater than this function, then this function here is big O of G. The reason why this is below is because O is at the upper part. I mean, G is above those. So we're talking about functions that don't grow as fast, which here I've written, they grow no faster than G of n. Yeah.
Yep.
Does that make sense?
Is that good as far as like time goes? Do you want it to be like big O versus omega? Is that what you're saying? You don't want it to grow any faster than the function?
Well, it's just putting an upper bound on it. So one of the things that's misleading, and we'll see an example of today, I can say something like, our best case is under these circumstances, and I still can put an upper bound, a lower bound, and an average case, or I mean a theta here, even though it's the best case scenario. There's times when that happens, right? Where you say like with certainty, it always takes 10 computations. Well, then it's always bounded above and below and at the same rate, right? Because you can always find that scalar multiple of that. That's that. But many times, if you look stuff up online, if you say, okay, for quicksort, what's the complexity of it? You're gonna see stuff almost exclusively in terms of big O. Because people really care about how quickly is it growing, because the worse that is, the longer it typically takes. You have a question?
I just feel it's irrelevant.
Oh, okay. All right. Other questions?
So we can do that as long as our two functions are in the same growth rate category, right?
Would that not be good?
So we can do the theta assumption as far as two functions that we have to compare as far as growth rate are in the same category of people.
Well, these are classes, right? So even though people you don't want to do this, because go back to my example of 1,000 mile per hour average speed. There's lots of things that are above n log n. So technically, if you're bounded above by n log n, you're also bounded above by n, and you're also bounded above by, or I mean, like n squared and n cubed and n to the fourth and n to the fifth. But as those get bigger, it's less meaningful. So you really want to get as tight as you can. But it's still a group membership, like a set theory membership thing, as opposed to an equality. It's sort of misleading, like I said, it's easy to look and go, well, yeah, but you said F was equal to 2n plus 3, and G is equal to n minus 6, so how can F be bounded above by G? Well, I can still find a scalar multiple of this that's going to make it above this at some point, right? What if I use 10? Well, 10n minus 60 at some point to be above this.
So would it be fair to assume, like, when it comes to a big O and a big I, that they're pretty much be the same family of functions as the G of n?
I'm not sure I understand what you mean by that.
Like, when you have like an exponential function, it's likely gonna be another exponential function, just.
Oh, yeah, yeah. So when we end up looking at stuff, going back to what I said last time about a rule of thumb, you know, if I say, okay, I got this loop here, that goes 1 to n, inside that's another loop, it goes 1 to n. So for the inner loop, it runs n times for every iteration of the outer loop. So I end up saying, okay, well, how many times does the inner part run? Well, it's n times n, right? So you get, okay, that's n squared, and so therefore it's big O n squared, if that's all we're looking at. Right. So let's see how we can come up doing some functions, instead of just trying to eyeball it. What are some ways to try to figure out what the relationship is? So here in our row, we know that f of n is big O of g of n if the limit as n approaches infinity of the ratio of f of n to g of n is this constant c. Okay? If you think about it, that goes back to what we had written before in our definition. We had the 0 less than or equal to f of n less than or equal to c times g for all n beyond n naught, right? So it's really just sort of the, take the ratio here, right? And note here it says c is a non-negative real number, so it could be 0. Okay? It's just finding one of these is a scalar multiple of the other, is really what it sort of says. All right? Let's look at an example. So here I give you two functions. G of n is equal to n cubed divided by 4. F of n is equal to 50 n squared plus 25n. If I were to just spot check and say, well, what if I chose n equals 1? We see G of n is going to be 1/4, while F of n is 75, right? But I'm arguing that G of n is an upper bound. Okay? So, but I can use that definition to check this, to see if it is upper bound. So limit as n approaches infinity, at the f of n divided by g of n. This way, make it more clear. So remember, that's really saying, well, C is a non-negative integer, so if I can get 0 and above, you know, then it says this is true. So if I were to look at this, we could break it down, but ultimately what's gonna matter here? Well, ultimately what's gonna matter is I'm gonna have n squared in the numerator, and I'm gonna have n cubed in the denominator, right? As n gets bigger. As n gets bigger, the 25n won't matter, this 50 won't matter, this 1/4 won't matter, which ultimately is moving to this, or sorry, 1 over n, so as n gets bigger, right, we're going to 0.
Yeah.
So the limit here is 0, which is a non-negative scalar. Therefore it is in big O of that. Okay. Well, it's a calculus problem here, Art, right? It's about taking the limits. I guess it's been a while since I took calculus, I'm trying to think what way, I don't know what way they teach in terms of limits. But for me, I basically look at what matters in the numerator is the n squared, what matters in the denominator is the n cubed. So ultimately, sorry, this was supposed to be this. It basically, basically it heads towards this, right? You see that? Which simplifies to this, so as n gets bigger, this fraction gets smaller, but it won't go below 0. Does that make sense to me?
Can we do the same? Can we do the same thing in our homeworks, when we can assume that only that matters and remove the middle part?
Yeah, I mean, I don't, like I said, I don't know what they teach. I took Cal 1 in '86, I think. Isaac Newton wasn't still around then, or not, but I know it was a while ago. So I don't know how they teach it now.
Yeah, but in the homework you say we have to prove our answers with the mathematical.
Right, don't just say, I prefer you not just say 0. I mean,
Okay.
for something like this, I mean, it's debatable how much work you need to show. For something I'm about to show you next, there's a lot more algebraic manipulation involved, so I would want to see more algebraic manipulation.
Professor, we can just divide by the largest power and it will give us the same result as 1 over n. But if we divide everything by n cubed, you'll end up with 1 over n.
Oh, yeah, multiply through basically that. Right, yeah. I mean, you do it in a variety of ways. At this point, I'm used to just sort of eyeballing things, you know, because I don't remember how they teach it. Right. But we said that when n was equal to 1, g is actually lower. Alright. So we're claiming, so we said over here where n equals 1, right, that g is actually lower than f. But if this statement's true, that f is big O of g, that means at some point, in not, c times g has to pass it, right? And what that means? By definition, that's what it means. Even though for some small numbers of n, f actually has the bigger value, we're talking about in the long haul that if you say, okay, n just keeps getting bigger and bigger, which is why we care about all this stuff. If you only had to do work with 10 objects, in the vast majority of cases, you wouldn't care which way you chose. It's because when you're talking about thousands, millions, billions, there are some exceptions. You start getting to factorials, you don't have to have, n doesn't have to be very big before it's already big, right? Because 10 factorial is 3.6 million, so it's already a lot. But for many things, you know, when you're talking about things in the millions or billions or more, well, that's a lot of stuff to work with, and therefore you want the more computationally efficient approach, okay? So we typically don't care about small numbers of things, okay? But this says at some point, if that's true, and we just demonstrated it was based on the definition, we said at some point g starts to grow at a faster rate than f, or at least f isn't any faster than g, that's probably a better way to state it. therefore it's big O. So where's this point at? Okay, well, this point has to be the point where the two functions are equal, right? So they cross over. When, make sure I write this in my order, so I'm copy this. G of n is equal to F of n. So let's find that and plug in some numbers and see there is a crossover point where it really does swap. And then once you see the numbers, you can get a better feel for why it has to also be true. All right? So here, I know the point where they cross over is where G and F have to have the same value, okay? So I can equate the two sides. I multiply 3 by 4 to get rid of the fraction over here, and now I've took the right side, brought it over the left side, and now it's a root finding problem, right? The thing they taught you in high school you thought you'd never need again, well, it's back, right? So it's a root finding problem now. So since this, the largest power here is 3, there's gonna be 3 roots, or they could be repeated. So the roots for this turn out to be 0, 200.5, and minus 0.5. All right. Now we don't care about the 0 part, because we technically start at n needs to be, if we're, depending on what we're doing, but in many cases, say for example, you're talking about sorting. Nobody says, how long does it take to sort 0 things, right? You always want it to be at least 2, but we're gonna start with the n equals 1. So this is out, which also means the negative one has to be out. Which means our crossover point is the 200.5. Now you may say, well, yeah, but you're saying n, for many things we do, n has to be an integer. How do you get 200.5? Because the math doesn't know what the underlying problem constraints are. It just says find the point where the two functions cross, all right? But I'm gonna evaluate it at integer values of n. That's what we're doing now. So I picked values of n that were in the proximity of 200.5. So you see the integer that's before 200.5, 200, we can see f of n is still greater than g of n. But then as soon as I hit 201, which is on the other side of the 200.5, now they've swapped. So now f is less than g, and it's going to continue that way. And if you go back to the function, if we think about big N again and say, okay, basically comparing n cubed to n squared, we realize at some point the n cubed has to take off compared to the n squared. Okay, so logically it should make sense.
So would this then be, so what is it, so f of n is growing faster than g of n? Or so?
No, g of n is growing
Oh,
faster than f of n,
Okay.
right?
So is
Or F is going, so it's kind of misleading. So it's better probably to say, and I keep doing the other one like you did. It's probably better to say what I had written before, which is F is not growing any faster than G of N. Because remember, we had a less than or equal. So I could have this, going back to what we said before. If I have F of N came down to be 2N plus 3, and G of N was equal to 6N minus 2. But both of these are big O of the other one. Because they're both N. Because I can always pick some scalar that pushes one of those above the other one, right? If I can find a C times the function to make it an upper bound, either of these could be bounded above by something. I know it messes with your head, but remember, it's not equality. It's about finding a scalar multiple of that function that pushes it above.
Okay.
You just have to mess with it enough to get used to that. But this also shows what's happening here. That's why I'm doing this, is that sure F was bigger up till this point. But because this right here is ultimately an N squared thing, and this is an N cubed thing, this has to be bigger, as long as you're using positive integers, or positive numbers, actually. It doesn't have to be integers, but yeah, right? You see that? Questions about that? Let's work with these same functions here. And ask the question, while I was writing here, can we say G of N is big O of our F of N? You already intuitively know the answer is no, but how would we show that? So the same F and G. All right. So by definition, if this is true, right? By definition, if this is true, then we're saying 0 is less than or equal to G of N, which is less than or equal to C times F of N for some N beyond N naught, or for some N naught when N is beyond that, right? If this is true, it's saying some scalar multiplier of our function F has to be an upper bound on our G, okay? So the way I'm gonna show that's not true is do something similar to what we did here. So N cubed by 4 is less than or equal to 50C N squared, because I'm multiplying through by C, is 25C N. All I did was take the right-hand side and multiply it by the C. Okay, so like this right here. G of N is less than or equal to C of F of N. Okay, I multiply through by the C. This becomes N cubed less than or equal to 200C N squared plus 100C N. Okay. And now if I divide N squared, I'm going to get N is less than or equal to 200C plus 100C divided by N. Okay? Everybody with me so far? Because now it's just algebra at this point. Okay? So what do we know about the right-hand side? I mean, other than it's a function of N, the left-hand side's a function of N. So we're gonna pick some value of C. It doesn't matter what it is, but once we pick it, it's stuck, right? It's a constant, okay? But N grows. So the numerator of the fraction will stay the same, but N is gonna grow. But we can simplify the right-hand side if we can figure out a bound on it, a lower bound or an upper bound, okay? So remember, our N is gonna be greater than or equal to 1 for what we're doing, okay? If N equals 1, then 100C divided by N is equal to 100C, right? And what happens after that is n gets bigger. 100c divided by n gets smaller. So that means this is maximized when n is equal to 1. Everybody see that?
Mhm.
So at this point on, the right-hand side gets smaller. So that means when n is equal to 1, this part here is less than or equal to 300c, because I'll have the 200c plus the 100c just becomes when n equals 1. All right? After this part gets smaller. But we can take that and say, okay, this means n is less than or equal to 300c, right? But we said c is a constant, whereas n grows. So what's the problem here in terms of our definition? Well, you pick some c, whether you pick 10, 1,000, a million, a billion, it doesn't matter. At some point, n is going to pass that. Which means there's some point where my n goes, remember n here is just my reduced form of my n cubed. So it's still representative of my function. So it means at some point my function passes this. So I don't have the part where I said, okay, at a certain point, I'm always bounded above by this. I'm showing you can't bound it above after some point.
But wouldn't it be just you're finding that specific C where it's true?
Sure. But for the definition, it says you pick any c that's it's non-negative, and you pick an n naught, and you're saying all n's beyond that, okay? The fact is, once you pick a c, I'll let you pick your c, but once you do that, I can find a value of n that's gonna be bigger than 300 times c. That's the issue. All you do, so if we go back to the function, so for the way we have this written here, you know, we're saying for this problem, where we're trying to bound it above, so here's my g of the n, here's my c times f of the n. All right, for this, if you pick a different c, all I do is shift this crossover point down, but at some point g is still gonna pass it. N cubed still has to beat n squared at some point. These other things, the 50 and the 25 and all this stuff right here, these obviously make the right-hand side bigger for some values of n. But what we're saying is you can get a value of n that ultimately passes that. And there's nothing you can do about that, because you can't keep changing the c because I pick a different value of n. N is the one that's allowed to get bigger. C has to be set. It's a constant. Does that make sense to everybody?
So in the first part of the question, we were asked if f of n is the big O of g of n, right?
Right.
And we saw that to be true, correct?
Right.
So the second part is almost trying to determine if theta exists, because we're gonna say that the opposite would be the same, right? Because essentially you're saying that it's also the upper bound of it, I guess? I don't know if the question makes sense.
I understand what you're saying. I'm sitting here thinking about it before I say something dumb. That's what I'm thinking. I mean, it's possible for f and g to both be in the same class, where they're both bounded above by the same thing, right? Because we get to pick those scalars that shift the functions up and down. Okay, so we get to pick that. So the fact that we found that f was big O of g doesn't rule out this. I'm trying to think, does that guarantee then the lower bound? I'm not willing to jump out there on that, answer your question.
So I know that in the previous, we took the limit.
Okay.
If we took the limit, this would go to infinity, right? So is that why would that be another way to
Right.
disprove it then? Or-
Right. I mean, you can do that and then see it's not gonna work, right? Yeah, because you don't get that constant. Because it's showing it, yeah, it grows too fast, because now you have the g in the numerator, f in the denominator, and you're showing that this grows without bound.
But showing that it goes to infinity.
Or I mean, yeah, the other direction, yeah. Does that make sense? All right. So we can do similar things for the other functions, or at least for omega. Let's look at that. So we have similar definitions to try to figure out what the omega is, and then you can combine those for the theta. If you want, we can call this F at the end, it doesn't matter. Most authors drop the end part and just say F or G. So this is saying F is big omega G of n. Remember, that means G is a lower bound. If the limit as n approaches infinity of the ratio of F to G is infinity, that is, F is growing much faster than G. Or if we get that they're a scalar multiple of each other, but that's greater than 0. Okay, so we're not going to, it's not like before where we're saying, okay, this one went to infinity, so this one has to go to 0 if we swap them, right? It could be this, because they could be similar functions, but one's just growing at a scalar multiple faster than the other one. Okay, that's where the C comes from. So let's look at one of these. Okay, so it's a sidebar, so this is the relevant math. Otherwise, you could be wondering where the magic came from. So I do 3 things on this to make it work. L'Hopital's rule. Recall this for situations where I get like an indeterminate form and I can't really work with it as is, so I take the first derivative of each of the functions and try to work with it. Okay, that's one thing. Another thing is this. There's the inverse relationship between these logs here. And the third thing. So if you're like me, I know a lot of logarithms lately, so I'm doing some Googling. Right? But ultimately, then I get this. So here's our example. Of course, we go back and look at that chart where we're comparing different functions in the order of growth. We should already have an idea that log of n is growing much slower than n squared, so it has to be true. But how do we show that? Using all the stuff I wrote over there. We'll get that. So of course, taking the derivative of n squared was easy, so the log n I had problems with. I remember that. If you use all these rules here, first we're using L'Hopital's rule to get to know to do something with this. Then I use the second and third things to figure out the denominator. Ultimately then, by the time you invert that, I get 2 times n squared times natural log of 2. So obviously as n squared increases there, it's heading towards infinity, right? Questions?
Logarithm is in base 2, correct?
Yes. Right, yeah, when we write just LG, that's gonna be our base 2 logarithm. Is that right? Log base 2 shows up a lot because of the way things get split in halves, so we're gonna see that a lot. Any other questions, sir? All right, let's start working with some code. Sorry. Let me write some comments over there so I can come back to this. All right. So. So strictly speaking, I don't know the true cost of these. Could you calculate it? Sure. Going back to what we said earlier, if I know what my compiler does to this, right, in terms of which assembly statements it transforms them into, and from my particular processor, this is all 20 through 12 stuff. For your particular processor, if you know that how many clock cycles it devotes to each of those assembly statements, that type of thing, if you know about pipelining and branch prediction, all these things that would really be too challenging to do in many cases, you could come up with an actual cost, but we can't reasonably do that, right? Especially stuff like the branch prediction and the pipelining and what's going to happen there. That's just going to be too challenging in most real world situations. So I'll make certain assumptions, all right? Anybody need this part here? All right. So we're going to make some assumptions. And that's what I did, so we get the same answers. That's what I did on your homework. I told you the cost. So what we're gonna do here is, I'm only gonna count my assumption here. I'm gonna say cost equals 1 when I less than n is evaluated. Notice here, I'm not even counting the I equals 0, the I plus plus. Of course, it should be obvious to you that as n gets really big, the I equals 0 part doesn't matter. But the I plus plus is going to execute about the same number of times as I less than n, right? So how's that effective? Well, if I counted the I plus plus, I basically doubled that component, but it's still a scalar multiple of that. So in terms of complexity, it won't matter, right? If I say in the end, this part right here evaluates to n cubed without this, well, I'll say, okay, well, I throw that in, that's gonna be 2 times n cubed, but still my big O is gonna say it's n cubed. So I don't really care about that part. Okay. So I made that assumption. The other assumption is I'm gonna say that's worth 1. So cost equals 1 each time evaluated, or each time processed, or how you wanna say it, executed. Okay. So those will be my assumptions in terms of cost. And it's a case to figure out how things work, all right? So, let's look at a couple things. How many times, so given n, okay, is, say non-negative, I guess technically it's always evaluated at least once. So we don't even have to have assumptions on whether n's positive or not. But how many times, if n is greater than 0, let's put it that way. If n is greater than 0, how many times is I less than n evaluated?
N times.
So is this a consensus? What are you saying? Or anybody?
Well, n minus one, yeah, n,
That's all I got, n minus 1.
because you can't do n, yeah, because I can't equal n.
No, but I starts at 0.
Oh, yeah.
Is one of these the answer?
Shouldn't we consider when we terminate the loop? Like when there's
Well, let's think
less than
about it.
12?
Let's say n equals 3, right? So 0 is less than 3, 1 is less than 3, 2 is less than 3. 3 is not less than 3, which is what breaks the test, right? So it's really n plus 1. Everybody see that?
Wouldn't it still be just like?
Because
n
it
though?
still runs.
Right, it's not gonna make a difference in the end, but if we're trying to get a true value. Okay. And we can, knowing a true value, I can tell you, we can actually verify it. Right. So let's create a table. Alright, so. So statement, I less than n, we said that's going to be evaluated n plus 1 times, right? Each time it's evaluated, the cost is 1. So the total cost here is n plus 1 for that statement. Everybody see that? Okay. Now what about the x equals x plus I? How many times is that evaluated? Now that is n, right? So x plus equal I, so that's n times 1, which is equal to n. So now my total cost is the sum of these. N plus 1 plus n, which is 2n plus 1. Everybody see that? If I say, okay, what's the big O of that? What function is an upper bound on that with some scalar multiple? Right. So this is big O of n. So this right here is really my f of n. Okay, if I say g of n is equal to n, can I pick something that's above this at some point? Yes. Okay, in fact, we check that. Let's not forget this. We'll do it here. Anybody still need this part? In fact, I got some numbers worked out. Let me see. Let C equals 3, and N naught equals 1. Remember our definition. It says if there's a scalar multiple of G, C, positive one actually, I guess here, and an N naught such that all the N's past that make G of N larger or greater than or equal, then we know it's true. So if we look at the table here. They're equal. So I found a C and I found an N naught where that relationship holds. And so we should realize that because the left-hand side is basically 2 times N and the right-hand side is 3 times N, for positive N's, 3 times is going to be greater than or equal, right? So we realize this less than relationship here between F and G has to continue. Right, we can see that. Everybody see that? which is also why we don't write this. So why didn't I say, well, this is 2n plus 1, so why didn't I say this is big O of 2n or big O of 2n plus 1? Well, once again, it's just a scalar multiple, right? It's really about the n part. That's the part that's changing. So as long as I can find the scalar multiple, you tend to simplify it. We don't care about the 2, we don't care about the 1. Just using n, I've already found a C and an n naught for which is homes. Here's where the crossover point is. Here's my n naught, right? They're both 3. And after this, G gets bigger, faster than F does. Therefore, I found the point. They actually both start at the same point, right here. There's my F, there's my CG. If I picked a different N naught and C, I could have a crossover effect, but still at some point, G is gonna pass F and be larger than F. Or at least as big as it.
So does that come from the definition of like getting
Right.
an O, right?
Right, right. Where I said big O of this means this. You have an F such that, right? There were constants C and N naught such that you had that relationship. That's what I've done here.
So it would be fair to say that any constants or scalables are basically arbitrary in this case?
Right. You never really see this. Well, I say never, almost never. Somebody may do it, but you're not really, see, the misconception is always that you're making it more precise, but you're not really making it more precise. It goes back to the asymptotic part of it. You're saying there's this function that grows, at least as fast or, at least as slow or whatever you're doing. Right. It's still really about putting a bound so that ultimately we can look at things and say, I can tell this is better than this, depending on what you mean by better. Questions on that? So for this one, before we leave. Oh, so we're gonna check, say, okay, so we're talking about, do I really need to include the n plus 1? Well, if I just said n and n, I still would've got 2n and it's still n, so it's fine. But if I really wanna check the calculations, say, well, what if n was, let's think how we do it. So we would have, so in terms of evaluating, let's say n equals 3. So here I would say 0 is less than 3, 1 is less than 3, 2 is less than 3, 3 is not less than 3. And then I would update this. So what's the total there? Well, when n was 3, I had 4 of the I less than n's, and I have 3 of the x plus equal i's. That's 7 things. 2 times 3 is 6 plus 1 is 7. There's my cost. That's the function of n. So they match is what I'm saying. My f of n, when I wrote it as 2n plus 1, is my true cost. If you say, tell me exactly, based on my assumption of the cost, how many of these things did I do? It really was 7 when n was equal to 3, right? But if you say, okay, bound it by something, now you're getting more of a ballpark type thing, well, yeah, it's n. It's bounded by n. Okay, so I'm just going to multiply that. Okay? Questions about that?
Can you explain again why the I plus L doesn't come into the equation?
I just chose to leave it out.
Okay.
If I could include it, but if you did that, then this would be 2 of these, right? So it would really be, well, I don't want to do your homework for you. So I threw in those extra things, your homework, just to give you more pieces moving so you can play with it. But it's just an assumption. I mean, the reality is most of the time when people look like this, they don't really count the 3 different parts because it's still a scalar multiple. If it was something else, like this had like an n squared part, obviously you can't leave that out. But including it basically just doubles the cost of this. That's really what it comes down to. And even then, like I said, when we get down to comparing actual functions, it doesn't matter what constant c you put in front of n, right? No matter how big you make it, it's still ultimately going to be less than n squared for some large positive value of n. So it doesn't matter. in terms of what we're trying to do. If I'm trying to do this part here, where I'm saying, tell me, okay, exactly how much did it cost? Yeah, it matters. And there are times when you'll see when people are looking at different algorithms, they say, well, sure, in general, this one's better than this one, but I'm not working with that many numbers, so the quote-unquote better one may have so much overhead that allows it to be better when N is really big. It hurts you when N is small. They do have some hybrid approaches to sorting where they'll say, sure, this approach, say, for example, they have lots of divide and conquer approaches where they say, we're gonna take the data and we split it into parts, we split those parts into parts, split those parts into parts, and you build a tree. And in general, they're faster than the ones that are like this, the bubble sort that are N squared. But then we get down to a point where one of those subparts has few enough elements that it makes sense to switch to the quote-unquote slower one because it's actually faster for small numbers. Other questions about that? Other questions about this? Oh, I was gonna say on that before we left. So once again, we have blue. Okay. So we found f of m was 2n plus 1 was the cost. Okay. So what's our best case scenario? Well, it still takes 2n plus 1, right? Which is big O of n. And what's our worst case? Well, it still takes 2n plus 1, which is big O of n. And on average, how long does this take? Well, it's still 2n plus 1, which is big O of n. And the point of that is there's a misconception that best means big O, worst means omega, and I don't know if this is supposed to be theta or whatever for average, but that's just not the case. It's about, is it an upper bound, is it a lower bound, is it a combination of the two, okay? In this case, it's effectively hard-coded. It has to run a certain number of times, right? There's no debate, there's nothing debatable about it. It's not like if you said, well, how long is it, how many different numbers will we have to swap if you're trying to sort some numbers? Well, it depends on the numbers, right? And the order they're in. If it's already sorted, you don't have to swap anything. And if it's completely the reverse direction of what you want, well, you swapping everything. So in those cases, now you do have an upper bound and a lower bound that may be different. Everybody see that? So they're not, these are not the same as these. Okay. So here we have a C function that's gonna search an array of ints looking for value. If it finds it, it's gonna return the index of that, right, which would be non-negative. If it makes it through the entire array and doesn't find value, it's gonna return -1 as a flag to say I couldn't find it, okay? Some people would call this a linear search, some people call it sequential search. But basically, I'm going through and looking, look at the first one, is this it? Look at the second one, is this it? Look at the third one, is this it? Until I find it or I get to the end, right? So for this, the only thing I'm gonna count in my cost is how many times do I ask, is D sub I equal to value? Can I throw other things in here? Sure. But in the end, it's not gonna change the big O part. Okay. So here I'm gonna say there's a cost of 1 each time this is evaluated. Meaning that if this part right here. Okay. Questions about that part? All right. So what's our best case scenario here? What's that?
Very close, maybe.
Yeah.
1, yeah.
D sub 0 contains value, right? Best case, D sub 0 is equal to value. Okay? So what's the cost of that?
1.
It's 1.
Just 1.
Even if we said the cost of this statement is 23, I still would write big O of 1. Okay? Because it's my simplest form of the function. Where here the function is just 1, it's a constant. It's a constant cost. So I'm gonna call that 1, even though the true cost may be 3 clock cycles, 8 clock cycles, I don't know what it is. It doesn't matter for what I'm doing here, okay? That's my best case scenario, okay? What's the worst case scenario?
Maybe. Up the end.
So for the entire array.
Exactly. We go through all n elements of the
And minus
array,
one.
asking a question. Is it there?
Minus
Is it
one.
there? Is it there? Right? So here you could get into a debate, well, do we consider, is there like a, if I was including the cost of return -1, if I was counting that cost, well then not being there would be an additional cost of one thing, whatever I say the cost that is. But I'm perfectly fine saying worst case is look at all n elements. And what's the big O of that? N. Right? Because it's a factor of how many elements are in the array. Surely you realize that if this array has 10 numbers in it, or it has 1 billion numbers in it, those aren't equal, right? It's a factor of how many numbers are there, which is n. Right? So it's big O of n. Right? Everybody with me so far? Because that was the easy ones. It's about to go downhill. Right? Average. Average is much more challenging, so let's look at that. I'm trying to think what I need here for the race. Anybody still need the code? Let's say this is our array. Okay. Right. In order to find the average, I'm going to have to make some assumptions. Okay? And why is that? Because when I'm talking about the average, you know, if for example, let's say you had a scenario where you knew 99% of the time the number you're looking for is not in the array. Well, then for all intents and purposes, you got your worst case, right? You're looking at everything that's there 99% of the time, right? On the other hand, if you said, well, what if the majority of the time, the thing you're looking for is in the first position? Well, now you got big O of 1 the vast majority of the time. So you gotta make some assumptions. Now, if you know something about a distribution that's involved, like, 12% of the time it's here, and 18% of the time it's here, and 23% of the time it's here, something like that, you can do something more complex, but your brain will explode trying to do that, right? So I'm gonna make certain assumptions. So my assumptions here, so the way I'm looking at this is I have n actual array elements, okay? Plus, I have what I'm calling my extra position is not in the array. I'm gonna treat them all equally weighted. Okay? So I'm gonna assume the probability of being in any particular array position or not in the array are equal. That is, in this case, I'm pretending like there's 5 positions, so I'm saying each one has a probability of 1/5. Everybody understand what I'm saying there? So if n was 4, the odds are 1/5 of any of these 5 scenarios occurring. It's in the first position, it's in the second position, third position, fourth position, or not in the array at all. Okay? Once again, if you had some reason to believe that that wasn't correct, you could do some other analysis. Okay? But it's obviously, the more they start to deviate from this, the more challenging it becomes to do the math. Okay? Everybody with me so far? All right, so let's see what happens. Let me start with an example. Let's say, keeping our costs, let's say you ran an experiment. So instead of trying to do analysis, in terms of doing the math, you're doing something like a Monte Carlo simulation, which means if I have an idea of what the distribution is, I'm gonna generate a random number from that distribution and use it. So I'm just gonna like make up some data. In this case, I'll make up data and say, how long does it take me to find something? Okay? And then maybe I make up some more data. And I say, how long does it take me to find something? I make up some more data and say, how long does it take me to find something? And then I figure out what the average is over all those little experiments, right? Each of those scenarios, and say, okay, this is my average cost. Okay? So imagine I did that. Let's say number of comparisons. All right, let's do it here. So. So I do it the first time, I find the number I'm looking for in the first array element. And then I do it again, and next time I have to look at 2 array elements to find what I'm looking for. And the next time it took 3. Okay, and I stop there and say, what was my average cost if each comparison counts 1? Oh, 1 plus 2 plus 3 divided by 3, 6 divided by 3, it would be 2. Right? I got these 3 different things. Those are the costs I happen to get. It averaged out to, it took me 2 comparisons for this scenario. Okay, everybody with me on that? All right. So now we know there's n elements here. So this is a legitimate way of doing things like this, or really something called Monte Carlo simulation, where they use it to evaluate integrals and things like that. If you're interested, you take computational methods. We talk about that more. But there's times when you have to do things like, for example, one of the places it would be used, like in place of integrals, would be, I give you this shape here. What's the area of it? Well, there may be functions that describe these, and in theory, you can take the integral of it and figure it out, but that's not gonna hurt your brain, right? But if you have a way of easily evaluating, generate, like throwing darts at it, you start looking at values here, and say what percentage end up here relative to the total thing, that gets you to estimate the area. Okay, that's one of the uses for Monte Carlo simulation. So you can do it with experiments like this, try it a million times and see how it works out. Okay. So we said there's n positions, so. So somebody didn't like Monte Carlo, or they often make some money? So if we're using C indexing, then an array of n values has indices from 0 to n minus 1, right? And so if our number happens to be in d sub 0, I did one comparison. If it was in d sub 1, I did 2 comparisons. D sub 2, I was in 3 comparisons. And if the number I was looking for was in the last array element, then I did n comparisons. Right? Everybody agree on that?
Yes.
All right? So I'll do these things, say, okay, thinking back to my experiment over there, what's the total cost? It's the average of this sum of costs. That's the average, right? And the reason I made this assumption was so I could weigh them equally. Okay, so what's the weight of each? 1/n. There's n of these. Well, we sit there and want their n, but n values. And each of those had the same odds. Now we could count the n times 1, but it won't change things. We could count them, oh, it wasn't in the array and I'll get the extra one, but it ultimately won't change the big O value, okay? But there's n of these, so it's just a case of figuring out what the sum is. So what is 1 plus 2 plus 3 plus da plus n? Hopefully you saw that in discrete structures. What's that?
Sum of all the
Yeah, n plus 1 by 2, something like that.
Right. We can spot check, it's not technically a proof, and say, okay, what about the first 3? 1 plus 2 plus 3 is 6. 3 times 4 is 12 divided by 2 is my 6. Okay? So this is my total cost, so the cost of these okay? So if I said, say I ran these experiments, and let's say I did n of these and it just happened to work out this way. This would be the total cost, right? But I want to find the average cost. And they each have a weight of 1/n, so the average cost is equal 1 times n times the total cost. For those of you down there, this works out to n over 2 plus 1/2, which is equal to 1/2 of n plus 1/2. So what's the big O? N. Right? It's a function of n. So my answer is, we put it in there. So the average is big O of n. Now, true cost, you assume if they're equally likely, then you assume on average, I really search about half of the elements, right? Sometimes they go past a half, sometimes they be less than half, but it probably makes sense to you that on average, I look at roughly half of these, right? So this works out to that, 1/2 n plus 1/2, big O of n.
So do we just ignore the plus 1/2 at the end because it just
Right. It's trivial. As the n gets bigger, that becomes it effectively does become N over two, right? You put 1 million in there, 1 million divided by 2 is 500,000 plus a half, it still makes it 500,000. Does that make sense to everybody?
Can you quickly explain,
Quickly? I don't know about that.
the discrete math you did at the end? I took
Okay.
like 2 semesters ago, so.
Alright. So the sum of the first n positive integers is n over n plus 1, or n times n plus 1 divided by 2. There's a story, so you made a mistake of asking. There's a story about Gauss. You heard this about Gauss? Allegedly, the mathematician Gauss was in school, and his teacher said, okay, to keep him busy, told him to sum the first 100 integers, and so he just came up with the formula and gave him the answer. But the proof is this, so you say n plus 1, so you have 1 plus 2 plus 3, or a proof, I should say, plus plus n. So then what they say is, okay, I have 1 through n, and if I were to add to that, I just take the numbers and do them in reverse order. Each of these is 1 and n. So 1 plus n, and 2 plus n minus 1 is 1 plus n, and so forth. There were n of those, but I added a copy of it, right? So I really have 2 times as much, so I divide by 2. That's Gauss's approach, apparently, or at least they claim. And this one's fairly easy to prove using induction, so that's why I think you might have seen it in discrete, because it's a common example for proof by induction. Questions on that? I don't want to get too far separated from the other sections, but I said that. Everybody's picking up. I'm trying to think if I want to jump out there because I don't, like I said, I don't want to get too far apart. Any questions about any stuff we talked about today? We are going to see some more induction. So we will do some stuff. So we will do some proofs. Oh, let me talk about that. I can't remember if I said that earlier. Let me tell you this, because since it's relevant to the exam, you might want to hear it. For a class like this, you do things where you drive certain things and do other things that aren't necessarily well suited for homework problems, in the sense of, if I drive something, like if I drive this formula here, you know, I'm not gonna say on your homework, okay, drive that formula, which means you copying what you copied from me in the first place and giving it back. That would make no sense, right? For me to ask you to replicate this on your homework. It might make sense to ask you to go on a test. So anything I talk about in class is fair game for exams, unless I tell you otherwise, okay? So don't just say, well, all he asked me to do on the homework was this thing, and so I ignore everything else he ever said. That probably won't turn out too well, okay? Everybody understand that? So you should make some effort. I'm not saying this particular thing, but I'm talking about, we're gonna do lots of things where you're driving things or coming up with stuff, just to explain why it's the way it is. I'm not gonna ask you on the homework to replicate a derivation, a specific derivation. I might ask you to do something new. That's a different story, right? But I'm not asking you to just regurgitate something verbatim on homework when all you do is take your notes and you scribe them, or if you're smart, you photocopy it and give it back to me, right? That wouldn't make any sense. But it doesn't mean for a test, I don't want to see you do it, okay? And I would tell you as a warning, because somebody was asking the other day about fixing problems, and a bunch of people make the same mistake. So last semester, in one of my classes, I spent a day and a half at least, or maybe 2 full lectures, driving some things that I said were really important to me, right? In fact, we talked about them all semester. And while I was doing that, I saw a lot of people on their phone. So guess what became a test problem that most people didn't know how to do? And I would guess out of about 50 people in the class, roughly 5 were able to replicate it. And all I asked them to do is regurgitate part of what I'd done in class. So it wasn't even like it was anything new, but maybe 5 out of 50 knew how to do it. So that meant 45 unhappy people. I didn't fix that. Because the fix to that is put away your phone, right? So anything I talked about is fair game. Questions?
I have a question about the exam. For each exam, we just, do the material based on that and then revise for the next exam?
Right,
Yeah.
probably wanna hear this question, since it's about test. Right. So typically what I do, in the vast majority of cases, each test picks up where the last test left off, right? Now, some things we do never go away, right? It's like in programming, you'll get to the part, you go, "Phew, I hope I never have to write those loops anymore." Loops are always there, right? And so some things we do here, there's some things you'll do and you'll talk about it once and we'll move on. They'll be like the bitwise operators of algorithms, where I'll talk about it once and we move on, never have to do it again. But there's other things where it's foundational, where you go, wow, I'm gonna need that every time I do a test, right? So we'll decide that when we get there. But in terms of how I do that, I was talking about this in the other section this morning. So there's a lot of what I do in classes is based upon my pet peeves as a student, things I didn't like. So one of those would be, oh, let me give you this homework, gentlemen. Do you wanna hear this, or? One of my pet peeves is somebody says, oh, let me give you this homework now, and next class we're gonna have a test, but the stuff on the homework is on the test, but the homework's not technically due until after the test. But of course, if you're smart, you gotta get ready for the test, which means you do the homework ahead of the test, right? That never made any sense to me. And likewise, saying, well, I'm gonna give you some homework that's relevant to the test, and you turn in the day of the test, so you don't have no time to talk about it after that, that also doesn't make any sense. But I can't waste a whole bunch of time, so I do this. You say, okay, here's the homework, so homework number 1. And we go to here and say, okay, homework number 2. There may be some time in here, and then we have a test. Okay, well, I can't skip this week or two in here, even though it's material that won't be until the next test, because we hadn't had time to have homework or let you really soak it up. It doesn't necessarily be on the homework, but you don't necessarily have time to soak it up. I don't want to talk about something today and say, okay, next test, you have to know it. Or I mean, next week, next class. You didn't give you time to talk to me or whatever you need to do to resolve it. But I can't waste that time. Okay, so that's the trade-off. So in this case right here, I would say, you know, if, say homework 3 starts here, well, then these will be the things that'll be subject to this test, but this material right here might be relevant to homework 3 and then the future test. Okay, there's a trade-off. We can either use our time and say, okay, right here is where we're gonna have the test as soon as you do this, but it doesn't give you time to say, hey, I went through the homework, I didn't understand these problems, could you talk about this again, or whatever. It doesn't give you an opportunity to do that, so I don't do it. But that's the trade-off. That means we gotta use this time. I always get, I don't say always, but sometimes somebody complains, wow, he kept talking about new stuff even after the last homework. Like, well, we don't all go on vacation for 2 weeks while we wait for the test. Okay, even though you might want to. That's how I do it. All right? Questions about that?
I mean, I have a different question, but, just a bucket question. So, what is it? When you said like, for the, what is it, like, big O of G of n if the limit of n equals infinity, if like,
Okay.
is that, it's like, what is it? You said that for C, it can be C for all non-negative real numbers, and then the other
Right.
one
Right.
for,
You can't get 0. So if you have something, so if I have a relationship, as n approaches infinity,
yeah,
right? If I have this and it equals 0 because the bottom is getting bigger much faster than the top, then that means when I swap them, then it has to be infinity, right?
right.
If I have, we get that, and if I swap them, I get that.
Well, what I'm asking.
But then
is
there's
that-
others where it's not 0, but it's
Yeah.
like 3. So if I say, okay, they're inverses, right?
Yeah, but they're both greater than 0 and they're real numbers.
Right.
So they can't be both, okay, so I'm just asking.
Well, these could
just
be
like-
big O of each other, because remember, it's all about F and C of G. Is there a scalar multiple? So I could say, well, how could, obviously 2n is above n, but how could n ever be above 2n? If you say, okay, this is my G, and that's my F, well, I get to pick the C, right? I get to pick the C times this function to make it an upper bound on this. Let's say C equals 3. Well, 3n is above 2n, right?
Right,
So therefore it is an upper bound. So both of these is an upper bound to the other one. Both of these is big O of the other one, because they both would be big O n. You say, well, yeah, but you said 2n, how can that be big O of n? Well, okay, pick a c that's greater than 2, and this is bigger than this.
I mean, but then, like, what is it, is this omega, whatever this is, it says that it's growing
Right, omega.
at least as fast, but down here it's like c is greater than, what is it, 0, so, but they can't be both omega and big O, because it can't be growing faster and not growing faster at the same time, but there's like, it's like 1.
Right, but
and it
remember
works for both
theta,
of
but
them.
remember when we get theta, like in this case, you'd have theta. Theta says, I think I had C1 here, C1 of G, C2 of G, but the same G, and F is somewhere in the middle, in that sense. So when we go back to the ones where I said best case, worst case, and average case were all big O of n, I really could have said this. Right? They were all bounded above and below by n when we had the nested loops, right? 2n plus 1, we had the 2n plus 1, and I just wrote it as big O of n. But n was also a lower bound, right? Because I can pick a scalar multiple that puts it below this function. I can put a c in front of my n such that it goes above 2n plus 1 and goes below 2n plus 1. But it's the same function n. So therefore I can use theta.
Basically what I'm asking is, on the first problem of the homework, what is it, using the limits, you can like prove both this and this. I was just asking if is that even possible? Or do you have to like, because.
Well, remember the definition of this. I think we gave a definition, it said if and only if you had F was big O of G and F was big theta, omega of G, were the same, you had the same G, then it was theta. So it is possible to be both.
Okay, but it has to be like exactly the same, I guess?
Well, the G has to be the same, the function itself.
The constant is the one that matters. Because he's asking about the first homework, the one that I asked at the beginning of the class, so in that case, that, it can be both of them, we can claim that it's also big O and big omega, right? As
It could
long as
be.
the constant
It could be,
is
but it has to be,
big
right?
O.
If I gave you n squared and the other one's n, that can't be both,
Yeah, but
right?
if both of them are n squared with different constant number, then that
Right.
can be done.
But if I were to ask you, we agree 2n plus 1 is big O of n, right?
Yeah.
But what's the lower bound on it? Also n.
Yeah.
If I were to plot 2n plus 1 and just plot n, wouldn't the n be below this? Well, yeah, n would be less than 2n, right?
Yeah.
Because I get to pick that scalar, I get to pick the c, right? Remember the one I wrote in the middle that you have here? What does it say here?
At
It
the
grows at the
same
same rate. So like in this picture here, here's my f. If this is a function of n, like in this case 2n plus 1, well if g is n, if I pick the right c2, that grows faster than this. And if I pick the right c1, that grows less than this. Therefore it's both. It's both n. So this right here was big O of n and big omega of n. And therefore it has to be big theta of n.
Okay.
For the problem, it doesn't mean both of them have to be true, right?
Basically.
I'm just asking you to check to see if both of them are true.
Is it basically asking if there's a, it's but like, okay.
I'm asking you this, I'm saying, okay, is F big O of the G I gave you? Then I also ask, is F big omega of the G I gave you?
Yes.
Either of those could be true and either of those could be false. It depends on the F and G I give you.
Okay.
If it turns out that it was both for the same function, then technically big theta would, if you look in Corman, they like to use theta a lot. And technically it is better in some sense because it tells you two things, whereas big O only tells you one thing. So in that sense, it's better, more accurate, let's put it that way. But I tend to just do big O because that's what most people focus on.
Is it kind of like, if you have a function, some functions are bounded above and always below, but there's functions that are bounded below and always above?
I think I would say for particular functions, you won't always have one function both can be above and below something, right? You just have certain things like when we look at, once again, if we're saying, here's log n, which grows very slowly, and here's n squared, N squared is gonna be above log n. So we could say log of n is big O of n squared, and n squared is big omega of log n. Right? And in that case, I can't take, there's no scalar you can pick that will make one of these swap their order overall. In the short term, you may be able to, right? You say, oh, well, from n equals 1 to 10, yeah, this one is bigger than this one. But at some point, it's never gonna always be there. There's no scalar I can put in front of log of n that's always gonna push it above n squared after a certain point.
So basically what I'm just asking is if C is, for both the two limits for the big O and the big omega, if C, like the number that you get for C, if it's not only a non-negative real number, but it's also greater than 0, then it can be both of them?
Yeah, it can be both. I
Okay.
mean,
How do we write it? If we wanna write something like that, how do we write it exactly?
well, then you write theta.
Okay.
Corman, if you look in the Corman book, they write lots of things. So for this problem we had here, they would just said it was theta n. That's how they would write it. Whereas I wrote it big O.
Should we provide a graph as well?
You don't have to, that's more of an aid to help you understand what's happening. Because you don't really know where the crossover point, most part, people don't care about where the crossover point is, right? You know, I was talking to somebody after the earlier section about what happens with this class and what's gonna happen when you graduate and that kind of thing. The reality is, very few people are gonna sit down and do their own calculations. You know, it's not gonna be that now every time you write a program, you sit down and start trying to do the big O analysis of it, right? That's not how it's gonna happen. But what will happen, hopefully, is that you think about certain things. So you say, well, instead of using the naive approach, which is I just try everything, I know there's a smarter way that's much more computationally efficient. And you do it that way instead of just saying, well, n's not gonna be very big, I hope, so I can get away with it. Because you can do that in school because you don't work with that much data. But in real world situations, it can matter, right? Where you have a lot more data. You got millions or billions of things, so you care. But another reason why you need to learn this stuff is because even if you say, well, yeah, but I'm sure there's libraries out there that do this for me, sure. But how do you compare them? You got a dozen different sorting algorithms. Which one do you use? If you don't know the difference between them in terms of performance, you may make a bad choice. For example, I use bubble sort versus quick sort, but what if your data is already close to being sorted? Well, then it's possible to write bubble sort where it goes through and says, I don't need to fix all these. Oh, I just move a couple of things then. I mean, think about it. If I give you a bunch of numbers here and told you to put them in sorted order, you would look through and go, these are all in order. Oh, these are out. I'll swap those two and I'm done, right? You wouldn't sit here and say, let me take that and put it over here, take this, put it over here, and do this here. But some sorting algorithms sort of scramble stuff in a sense because they start breaking it up into sub pieces and then they go back and try to put things back in order. So it may actually be more work in those cases. But if you don't know any of these things, I like to say, the chickens at the fair play tic-tac-toe. You're kind of like that. You're just typing and hoping magic happens and, that's what it works. I don't know if I answered your question.
Yeah, it's just, I'm trying to figure out how something can not only be getting.
Be an upper bound and a lower bound?
Yeah, because whenever I do the math, it looks like it should only be getting bigger, but if I do the limit, it says it should work for both.
Well, you need to play with it, right? That's the reason I give you problems, so you can play with the actual numbers and see what's happening.
Okay.
And there's no guarantee there that the answer for both those is, yes, it's big O and big omega, or that it's either. And plus, like I showed something earlier, if you have functions that do this, well, that's neither, right? Because sometimes it's above, sometimes below, it just cycles back and forth. So there are functions that cycle back and forth between values. You can't pick something that's right through the middle of that and say, well, it looks like it's above it. No way it's below it. No way it's above it. It's not like you have big O, little, big O here, big omega here, big O here, big omega here. It doesn't work that way. Play with the numbers and see if that answers some of your questions. That's the point of working through it, is start getting these things to set your brain.
So then, the limits, are they just saying it could be this, or are they saying it is like big O, or?
We're saying it is.
Okay, so like it's, okay.
And part of that goes back to, if you look at examples like what I did over here, I mean, surely you realize if I have n divided by n squared, right? You could throw in some other constants, you know, what if the n has plus 1,000,000 or whatever? But you have to realize as n gets bigger, this ratio gets smaller and smaller, right? If n is a positive integer, n squared dwarfs n, right? I mean, throw some numbers in there. 10 divided by 100, you know, 1,000 divided by 1,000,000. It just gets worse, but it's never gonna go below 0.
So, does that open you up, because essentially you said the math, you wanted some kind of mathematical interpretation on the homework. So when essentially like a guess and check sort of approach be sufficient? So if you plugged in a number and you could say, hey, look, this happens here, so I can.
So
prove
it
at least
depends,
happens.
I mean, when you're doing limits or somewhat limited on
Right.
what I'm expecting somebody to write, the thing you have to be careful of with the plug some numbers in as proof
Right.
is those situations where it really doesn't prove it, like what we saw before. We said, okay, if I pick certain values of n, f was above g, and I pick other values of n, now g is above n.
Right.
So which one is the upper bound?
So,
Right?
so you're not looking for a proof per se, but you're looking for.
Well, the
some-
limits are sort of proving it.
Right.
I mean, the other things are helping you to get a feel for it, see, oh, I can see how these are growing.
Okay.
That's why I like that. It's about trying to get you to get some intuition, right? Where you can sort of see, because I was telling somebody earlier, I took this class, I took 20 through 20 in 1996. And I took the grad level version in 1999. So after that, you know, at some point, I couldn't put a number to things, but what it did do is change the way I looked at code. So I could look at two different pieces of code and say, I can't tell you what the big O of these are, but I can just tell you this has to be faster than this. I just realize it because I can look at how many nested loops are involved and things like that and get a feel for it, even if I can't quantify it. And that's one of the things I want people to get from the class. Like I said, when you get a job, or even after you leave this class, you're not gonna be sitting down and calculating big O values all the time. I don't believe that. I don't know if anybody does. But you should have a feel for it so you know how to do things that are more optimal than other things. Okay? Try playing with the numbers and see if that answers some of your questions. Next week.